Now look, I'll make you a promise. I know I'm standing between you and a wine or a beer, so I'm going to keep this one on track, and you can ask me questions when I've got a beer in my hand. So today I'm going to be, So I'm presenting a case study from a project and a paper that I co-authored with Charles Webster, and it's what we did when we did a electrical resilience upgrade up at the Hervey Bay Hospital in sunny part of Queensland, even a bit more north from here. And in terms of like what David Gray talked about, there was a couple of similarities which I'm going to talk about, which is going to be like some of the underlying reasoning why this design is actually so different and why it is so important that it is seriously looked at for future and upcoming hospitals. Because let's face it, if the power turns off, you ain't going to be sterilising, you ain't going to be doing much in a hospital. So it's a really important little part of the scheme. So back in 2014, 2015, one of the state health services actually went out and did a very comprehensive audit of all of their electrical infrastructure. So they looked at all their main switchboards, all their generators, all the distribution boards, and all the associated things that tied up around it, like controllers and whatnot. And what they found was that there was a common problem across the entire asset base. So across 16 health districts and quite a large number of buildings, there was like a couple of real common issues that they found. So what they found was that the majority, and when I mean majority, I mean almost every single main switchboard, had not had any prescribed maintenance, even though it actually does exist in the Australian standards, and it obviously exists in the OEM manuals that you get. Now, the reason for this was like if we go back 20 years, you could do live work. Today, you're not allowed to do any live electrical work. So what they found was, because to shut down the board, you had to then cause interruptions to the operations in the hospital. The shutdown never got done, so then the maintenance got deferred, and every time this maintenance got deferred, it just started adding and adding up. And in their report, they actually noted that some of these main switchboards were actually at a severe risk of arc flash. Now, if that went off, your hospitals, you're going to be taking stuff home because you're not going to get that hospital online very quickly. And of course, this is the compound effect, so the longer you delay, the worse it gets. The other thing they found was there was all of these magic little black boxes around called PLCs. And when they spoke to the people at the hospital, nobody actually knew what this black box did. There wasn't sufficient documentation to explain what this black box did. And in some cases, they said, well, it was only the original programmer from some integrator. Oh, we have to call him every time we need something done. In some cases, that person was, well and truly not working anymore. They're off on their caravan around Australia. So there was a real risk in terms of like this little black box, which is a really critical element, would mean that you would not have any automatic controls in an outage, and you would have to have a really, really comprehensive manual backup plan in place that everybody's familiar with. And then the other one was knowledge loss. So can I have hands up, please? Who actually has 100% accurate electrical single-line drawings in their... Sorry to ask the question I knew the answer for. So there was a lot of deficiencies in knowledge capture, right? Like, and I've faced it all the time when we walk around a site. The drawing says the board's called, DB, elec, and then I'm looking around. The only board I can see is called, primary healthcare. It's really a bit of a challenge. Now that becomes a bit of a problem, right? Because now you haven't been able to maintain your equipment, so you have a major fault. The PLC doesn't work properly, and now you're trying to rely on drawings to get this hospital back up that aren't accurate. So it's quite a horrible position to be in. Now, The reason that these things are not being maintained is actually baked into the design. So does anybody recognise that electrical architecture there where you have a switchboard with an automatic transfer switch, and then you have your utility and your generator, and potentially a bus tie between the two boards? And so if the utility fails, the generator starts, the ATS puts the load onto MSB1, and then that brings your backup system online. So this is an N+1, right? Easy peasy. But tell me, can anyone, and you know, sometimes you see these little challenges come up on like LinkedIn. You know, this is a question that Google uses when hiring someone. Can someone please tell me how I could keep that part of my hospital online and do work on MSB1 at the same time? Yes. Not easily, right? Like it can be done. It's going to be really disruptive. It's going to take a lot of time, and it's not going to be, you know, not going to be easy. So this problem's going to get compounded because, you know, we were talking earlier about sustainability. So one of the things towards sustainability is we have to migrate away from, you know, gas and coal. Believe it or not, I've got one customer who still uses coal, and obviously electrify everything. So this is actually going to make the challenge worse for all of us, because you've got a number of services today that are running on gas, so they're not impacted if you want to request a board shutdown to do some maintenance. But once that's been electrified, and now the entire kitchen and all the ovens are running electric, if you need to shut off the power, you're shutting down a lot more. So similarly, if there's an issue now on the electrical system because it hasn't been maintained and it's been put into a poor condition and hence a high risk, the blast radius is now greatly expanded. So, armed with that information, Charlie's team and the Hexeis team, we put our heads together and we came up with a different answer to what we see today. And we asked ourselves one question: how can we make a system that is going to be maintainable, easy to expand, and captures knowledge as it goes? So this is what the design looks, obviously very, very simplified. Basically, all we did is we moved the ATSs to below the main switchboard. So what we can do now up at Hervey Bay, and we've got about 40 of these ATSs now across the hospital. So what can happen now is if we want to do maintenance on MSB1, we basically just throw the switch, and these ATSs will transfer all of those downstream loads onto the generator. That transfer can happen in a matter of seconds. You then have a fully isolated MSB4, so including MEN, so it's a dual MEN system, and you can now get in there and do all the maintenance you need on that main switchboard, and then when you finish, you re-energize, and these all take the load back to the transformer. And hence, a very simple design has now taken care of a really big problem. So up at Hervey Bay, we can do, and they do main switchboard maintenance at any time as needed. And to the point that they actually do a monthly black start test. So not once a year, not once maybe every 10 years, they do it every single month. And at the beginning there, I did actually have a little presentation, which was a video being shot inside one of the wards, which actually showed them when they went from generator back to mains. Because a key thing on this system is it's a open transfer. So for those of you who don't know what open transfer means, a lot of hospital systems, when you want to go from generator back to the mains, your generator and the mains get connected in parallel, and then you disconnect the generator and then you're left on the mains. This open transfer, what we do is if we're running on the generator, we disconnect the generator and then very quickly connect the mains. Now, this is a very fast transfer system. So a lot of people were going like, oh, how can you turn the power off and not cause any problems? The transfer speed of the switch is within the voltage sag tolerance of equipment. So because it's so fast and it's in sync, it basically happens like that. And all of the interlocking in the system is in a way that it is actually mechanically impossible to ever parallel up to energy sources. So we actually have also eliminated another risk, which I've actually personally experienced. When we had a generator was parallel to the mains, there was a nearby grid fault, and it took out the mains and the generator. And the hospital nearly went, well, it did go black, like people were running because they had to go down and reset a whole bunch of protection relays. So the other problem I mentioned was PLCs, right? Who's got black box PLCs on their site? Who knows what they do? Okay, so one. So basically, what we did here is, it was a really simple answer in the end, but I can tell you now it took a lot of thinking, is we actually implemented the system with no PLCs. So we kept each vendor in their sandbox. So Schneider Electric for power quality management and metering and smart circuit breakers, ABB True One ATSs for doing rapid ATS transfers, and ComApp doing the power station control. And it's just hard wiring in between all of those systems. You've got 40 ATSs, so to give you an idea, inside every ATS, you've got this function called a timer. So each ATS has their timer set, so when they're transferring on and off loads, that timer controls the steps. You know, we didn't have to have a master PLC to sort of coordinate all this. The functionality the hospital needed was already purchased when they purchased that ATS. And we find that a lot in a lot of systems. There's a lot of latent functionality that you've procured but you're not actually using because your designers sort of just do it the way they did the last 10 jobs. The biggest benefit for that is the software you are using now is software that is developed by professional organisations, not some small integrator firm. It's maintained and supported by professional organisations in terms of cybersecurity, bugging, defects, life cycle support. So you get all those benefits for free, fundamentally. And because this actually all comes together without any black box, and you can get all the user manuals, you can get any technician or any integrator on site to help work with it. So another element of the design, which Charlie asked me to mention, was he also likes to make sure that when you put in your generators, you don't do like, 2 generators, you always go 3 generators at 60% each. Because that way you can take 1 generator out for maintenance and you've still got 120% capacity online. Whereas if you only have 2, you take 1 out, now you're talking about doing all sorts of fancy load shedding and contingencies in case something happens while that was happening. So the next bit is we rolled out what's called an energy infrastructure management system. So this sits over the top of all those systems and it just brings all their data back for reading. It's not used for controls, it's not used for operations, it's just used to give visualization. So this is the actual, sorry, wrong one. This is the actual screenshot from Harvey Bay, obviously. So basically we're showing the condition of all the breakers, the position of all the ATSs, power quality information. That's all live and running. And now that that's been installed, the electricians, the BEMS teams, they've all now started to use this constantly because at their fingertips, they go, they get some consultants say, what was the protection setting on that main breaker there? They can just click on it and it brings up the live protection settings. It's all there. It's not in documentation. There's actually been a secondary benefit, which we talked about in the beginning, which was that knowledge base. So because we're keeping this is live and linked to the system, as they've been adding new boards and modifying boards and doing the inevitable changes, this all gets updated as we go. So we're not relying on someone to update as-builts. We've now got real as-builts, which are animated. So that's actually solved that problem. The other benefit they have now is, because we've now got all this visibility across their electrical assets, is we can actually move and make savings and improve reliability for maintenance. So no longer do you have to just do simple program maintenance. Because, for example, with the breakers, we can get an aging report. So if you've got, say, 15 breakers are coming up for, the calendar says to do them, we can actually put them through the aging report, and you may find that you've only got to really do 2. Similarly, if you're still 6 months away from your next maintenance and one of them comes up as a red, you can get in there and fix it before it becomes a problem. And of course, we do this across your whole asset base. I have one case where not long after we put the system in, the client actually found that one of their sub-mains was actually running above rating. And it's because people in the ward have been adding loads without letting them know. And so it wasn't high enough to trip, but it was high enough to basically make everything super hot. And because everything was super hot, they were probably going to get half the life out of that sub-main cable if it had been left much longer. But because we now could catch it, we could fix it and prevent that early failure. So a question I really want to have everyone to sort of walk away from this is then this goes for engineers, directors, BEMS teams, don't ask, is my system N+1, right? That's kind of a taken, it has to be. Ask yourself, is my question expandable? Is this system maintainable? And is the system got intelligence? And of those ones, maintainable is number one. If it's not maintainable, send the design back to the drawing board and get them to come back and explain to you how it is actually maintainable. So fundamentally, make sure your designs are actually designed for operations. I mean, let's face it, a hospital's different to doing a design for a shopping centre or an office or a factory, right? You can shut those things down anytime. Hospitals, you try to shut down one of the wards, and then all of a sudden there's ramping at the hospital. What the kingmakers are going to say. They're going to say, no, you can't do that maintenance. I don't want to be in the paper. Leverage proven technology more. Don't take the so-called easy way out of going, just whack a PLC in and we'll just work around everything. Make people think, look at what you've got in your stuff and figure out how to connect it all up. That's what we did at Harvey Bay, and it works. And obviously look for data-driven intelligence. So since we did the Harvey Bay project, they've put 2 new buildings on site, so they've expanded the system. When they expanded the system, there was no re-engineering required. It was simply the project simply added to the existing system using the same architecture. They didn't have to go back and modify existing code, and they've added a 5th generator. And they've done that without having to modify anything that was already done before. So it's been proven. We've also now since rolled it out to Boona Hospital, another major acute hospital, and also Maryborough. Now, it's not all easy, so there's a couple of things we're having to do. Number one is we're lobbying to get the AS 3009 finally updated. It's really old, and it was written before we had things such as these rapid open transfer ATSs. And we also are looking at AS 3000 because this is a dual MEN architecture. So on these projects, we have had to sort of do a bit of a compliance pathway, but we've been through it a few times and it's gone through every time. Thank you very much.